want to welcome everyone to our prospective student virtual visit of 2022. My name is Philip Guerrero. I'm the graduate coordinator in the department, and I welcome you all again. All of you should have seen the schedule, but just in case you didn't, we'll start with a welcome and some information sessions from myself, from Brian Horton, the grad advisor, and most importantly, the dean, Claudia Mora. And then after that, we'll transition into our research theme summaries and have 6 different presenters telling you about the different research themes that exist here in the Jackson School and what's going on in those areas. So with that, I want to go ahead and introduce Dean Claudia Mora to address you all.
As Philip said, my name is Claudia Mora, and I've been the dean here at the Jackson School for about 2 years, almost exactly 2 years now. And the first thing I want to say is, is pretty much a motto these days in all geoscience departments, and that is that the world really needs geoscientists. And this is something that I think a lot of people have forgotten. They don't recognize the full breadth of what geoscience is or what geoscientists do. But we have a host of challenges facing society over the next few decades, whether it's how to mitigate and manage the impacts of climate change, to negotiate an energy transition towards a more carbon neutral world. And then we have a host of environmental and climatic challenges, including drought and extreme storms and fire. So where there's a challenge, there's an opportunity for geoscientists. And whether you are a person who's going to be looking into resourcing future generations, whether your interests are in Arctic warming, or in ocean science, or in earthquake hazards, and whether you work on that from a fundamental aspect or in a more applied aspect, the world needs you, and we need your skills. And I think what everyone at the Jackson School wants to do is to help you with your educational base, help you gain the knowledge that you'll need to work in whatever path you take, and to really launch you as you leave the school. So we're very glad you're here. And if you have any friends, you should probably invite them along too. The first question I want to address is, what is the Jackson School? Because a lot of people will say the Jackson School, but they really mean one or another of the units within the Jackson School. The Jackson School is only about 16 years old. It was formed by pulling together the geoscience units that were surrounding or on in the UT Austin campus. And it was founded largely on the very generous gift of Jack and Katie Jackson. And so this gift was used to unite these different units, the Department of Geological Sciences, the Bureau of Economic Geology, and the UT Institute for Geophysics, in the hopes that the sum would be greater, the sum is greater than the whole is greater than the sum of the parts. There you go, I could get it. So let me just explain how different these units are, because many people don't appreciate the differences between them. The students all will be attending the Department of Geological Sciences, in the sense that that's the degree granting unit. And DGS is among the largest and most academically diverse academic programs in the world. We have about 50 faculty. And our faculty have a global presence in field analytical and computational geoscience. In fact, the Jackson School is ranked #1 for its geology programs, #7 for its geophysics programs in the world, or in the US, sorry. The Bureau of Economic Geology is almost as old as the department itself. The Bureau conducts research that's primarily at the intersection of energy, environment, and the economy. And BEG BEG does fundamental or does research, but it tends to do research that is solution driven, and it's funded by federal and state agencies like DOE, the state of Texas. It partners with other academic institutes. We have quite a few industry associates. So these are consortia, in the industry consortia, for whom the BEG conducts relevant research. And it also serves as the State Geological Survey of Texas. And finally, the third unit is the UT Institute for Geophysics, or UTIG. This was first founded by Maurice Ewing, who was one of the most prominent geophysicists in recent history. And UTIG works across a very broad range of geophysics, including climate, polar geophysics, energy, marine geosciences, tectonophysics, and planetary physics. And it's especially known for expeditionary scale research at both the poles and on planetary bodies. So the point I want to make here is that as a student in the Jackson School, you can access science and advisors across all of these units. And so this gives you a special degree of flexibility in terms of what you want to do, and access to a far deeper pool of scientists than you would find at most universities. We are present on the main campus, which is close to downtown Austin, and also on a research campus that's about 9 miles to the north. The main campus, this is the Jackson Geoscience building, and this includes both well-equipped instructional laboratories and scientific and analytical laboratories, including, for example, our computed tomography center. The Pickle Research Campus actually has more square footage. It includes the BEG, which sits in this building over here. And also, let me see if I can get there it is. It sits on here, and then next to it is UTIG. And we have special laboratories at Pickle, including this flume and sedimentary pool. And we have the BEG hosts probably the largest institutional core facility in the world. We have across 3 different core facilities, we have almost 2 million boxes of core. The largest of the facilities is in Houston, but we also have a large facility in Austin. And these include cores not only from Texas, but from across the world. So one thing you're probably seeing that the Jackson School is bigger than most places that you might be considering. We have 50 faculty with 90 research scientists and 100 supporting research staff and postdocs. There's about 200 graduate students and 200 undergraduates. And that's a big institute, a big organization. UT Austin is also very large. There are 51,000 students here. About a fifth of them are graduate students. It is a top 10 public university. It has 48 top 10 programs. And it's in Austin, which is the tech boom center of the country right now. So a lot, they say everything is big about Texas. I don't believe it, because I once went to a swim meet in Texas and the medals were the size of my thumbprint. It was tiny, but we are large. Texas Geoscience is large. And I think if you're contemplating for a graduate school, you want to think about a large program. A large program benefits you. And we can benefit you both in our excellence across the board in all areas, the breadth of science that we do, the resources that we have through the Jackson Endowment, and all that adds up to the prestige of the university, which is always very helpful to you as you move on and look for a job. Let's see. As well, you'll probably, one of the reasons that you want a big program is because as a graduate student, you're going to learn as much from your peers as you will from any book, class, lecture, and I dare say mentor. And so by having 200 peers around you, you will find a peer group with whom you can study, learn, and bounce ideas off of. And if you work really hard, you can earn your halo. So at the Jackson School, what we're seeking to address fundamental geoscience questions regarding Earth's transitions over space and time. We're very interested in leading transformative and convergent research, that is multidisciplinary research that directly relates to societal challenges. We'd like to foster a diverse community of scholars that includes collaborative research groups that promote your world-class education. And what we really want to do is create the geoscience leaders of the future. And so when you come in here, that's our modest expectation of you. You will lead the science in a few years. You'll work with your mentors to identify significant research questions. Don't bother doing research unless you're answering an important question. You'll present your research at professional meetings. You'll be expected to publish your research results. You'll take classes, and you're going to build strength in a discipline and yet also learn to work in interdisciplinary teams. You're going to have lots of practice giving talks and teaching, becoming an effective communicator, becoming a creative thinker. And what we hope is that you find a career and employment that meets your goal, whatever that path may be. There was recently an interesting study conducted or supported by NSF. It was a graduate student, it examined the future of graduate geoscience education. And it had one important concept that came out very clearly, and that is that in the past, there was always a gap between people's formal education, their book learning, if you will, and what people would do as a professional employment. And that was professional employment could be in industry or in academia. And what fills that gap are applied skills in things like critical thinking and working with data and field skills and non-technical skills. And one of the most damning things that an employer said at this summit was that the US graduate programs are producing outstanding scientists, the very best that they'd seen, but they don't know how to do anything. And so if we want to do one thing with your education here at the Jackson School is to make sure that no one ever says this about you. We are going to focus on developing these important skills so that when you launch, you truly have the skills necessary to succeed in whatever area you wish. The research environment, you'll see as you come, is really changing quite a bit. And everyone's adjusting to this. There's a somewhat of a de-emphasis on the individual science project and a real emphasis, especially in very recent grants, in expanding the geoscience workforce, expanding it to be much more inclusive and diverse than it is. And also in working across disciplines, not just geoscience disciplines, but natural science to social science disciplines to try to address challenges like seafloor or sea level change and global change. So as you come in, you will see that the funding environment, the science environment around you is changing. It's a very exciting time, a little bit of an uncertain time, but you'll be surrounded by a lot of professionals who will help you negotiate this. It's important that you learn, I think, how different disciplines feed into research themes. So in a research theme, you might say, I'm a geochemist. These days, that could mean one of 10,000 things. You might be working on changes in sea temperature or salinity or acidity. You might be working on lunar samples in solid earth, in speleothems or cave deposits. In other words, geochemistry is a tool. It's an approach and a thought, a way to think, a way to approach geoscience problems from a chemical perspective. But that's about the only way that it's limited. Similarly, when you start to think about specific problems or research themes, that's where you realize how many different disciplines in geology go into the same study. Texas had a 2011 drought that was extreme. It was the most extreme drought probably, or in recorded history for Texas. And this drought has been studied. Can be studied, or drought patterns in general can be studied through geochemistry, through hydrology, through geophysics, through paleontology. So again, as you go through in a large department or a large school like the Jackson School, I think one of the things that you will see is how many different ways people address the general problems in geoscience. And I hope that gets you really excited about the potential for your education here. I'm going to skip that. So so I guess what I want to say is we're really glad you're here. I'm really happy that you're considering the school. It's a terrific school. The state of Texas is a very large state. If you drive from Houston to El Paso, it takes about the same amount of time as it takes to drive from El Paso to Los Angeles and California. And the geology of Texas is quite variable, although more horizontally than vertically, unless you go subsurface. But we want you to enjoy the ride, and we want you to emerge as capable a scientist as you can. We have a lot of things in Texas, from level land. If you've never been to level land, it's over here, over here near Midland. We have gorgeous areas like Big Bend, oh gosh, I'm spacing out the name of these mountains. I'll come up with it. In the
Guadalupe.
Guadalupe. There, no, is that Guadalupe? Yeah, it is. Many of you will go on field trips there. And so I'm just showing you some geology. That Texas does have wonderful geology. There's Guadalupe. Does have wonderful geology, and as a student here, you will likely go to all of these places to explore the geology of the state. This is very close to Austin. This is Enchanted Rock Batholith, where it's traditional that we hike you up to the top of this on the very hottest day of August and muggiest day of August. We also have a long coastline that's being challenged by sea level change. And right here in Austin, we have some lovely swimming springs and things like that. And Austin's a wonderful place to live. Texas is geologically interesting. It's a microcosm. The state of Texas geologically is a microcosm for the entire world right now. If there's a challenge that the world is facing, Texas is facing it. Texas is the second highest burn risk, wildland fire risk to Southern California. So after Northern California, since it's mostly burned down, then maybe Southern California will burn down, and then you'll see most of Texas in challenge. So if there's an issue faced by the globe, it's faced by the state of Texas. And if you're interested in learning of the geoscience that will help you resolve many of these issues, I think one of the best places you can do it is here at the Jackson School. So I'll stop there. And one thing you need to know is we do say y'all in Texas. Y'all is not plural. Y'all is singular. The plural for y'all is all y'all. So all y'all, I'm all done.
I'd like to introduce Dr. Brian Horton, who is the graduate advisor of the program. The graduate advisor is a faculty member who oversees all aspects of the graduate program. So he oversees everyone's individual program, like I said, but is also there to deal with anybody who has problems with their degree or, excuse me, needs to do things like petition the graduate school for different kinds of course requirements, things like that. So I will let Brian go ahead and take it away.
Okay, thank you. Welcome, everyone. My name is Brian Horton. I am the graduate advisor. So you can see the schedule listed there on the screen. We want to go through some of these overview elements before we jump in at 9:45, jumping into those 6 different research presentations. So a little bit of this is more on the administrative side, but the awarding of degrees, graduate degrees, masters, and PhDs, those come from the UT Graduate School. So my role as the graduate advisor is as someone that's here to help you. So the idea is that we will help you get towards finishing those degrees. So I'm the graduate advisor. I'm also the chair of this UT Graduate School Committee. This is sort of a formal administrative committee called the Graduate Studies Committee, but you will hear about this as a member of the Jackson School. The Graduate Studies Committee, the GSC, we oversee the awarding of degrees in terms of making the rules about what's required. And that includes not only coursework, but of course your master's thesis or your doctoral dissertation. For the PhD, you write a dissertation. For the master's, you write a master's thesis. There's also various exams, such as the qualifying exam for PhD students and a variety of different procedures. So all of that is overseen by this group, this Graduate Studies Committee. And I am the current chair of that committee. And also I'm known as the graduate advisor. So the GSC, now this includes all of the faculty that are in the Department of Geological Sciences, and it also includes a number of research scientists who are at the BEG or UTIG. So it involves all components of the Jackson School of Geosciences. So the 2 important individuals, again, we're here to help, include the graduate advisor, that's currently me, and the graduate coordinator, that's Philip Guerrero. So we're responsible for all these different things that are listed on the slide. So the point here is that you're going to move from an undergraduate program into a graduate program, and the rules are entirely different. You know, undergraduate work was dominantly based on the coursework, the classes that you completed, and graduate programs involve some amount of coursework, but really so much of the focus is on the research project that you will be participating in. So we're here to help, the graduate advisor and the graduate coordinator. And to boil it down more simply, the #1 point person for you in terms of questions that you may have, almost certainly, because he's the person who has the answers, is Philip Guerrero, the graduate coordinator. Now, we've spent over the last couple of years, the GSC has taken a lot of time to properly get our website whipped into shape. So as a prospective graduate student, I encourage you to go to this website and you can click on any number of these different links and read about a whole range of different procedures and processes and areas that we're able to help. So if there's an issue that you have or a question, this is commonly the starting point. So I'm showing the first slide here is just the first part of this website. You can see that they're coordinated into these different topics. There's the latest in terms of the COVID-19 policies, but also the issue of advising research and career services. We have an entire career services program here to help you make plans for your career beyond your graduate degree. We have a whole list of features related to our facilities within the Jackson School. Within the graduate program, there's a really vital resource, and that is the handbook. It must be 35 pages long now, single spaced. It's full of all of the details that you need to get you through your master's or PhD. There's a lot of individual efforts that have to be made, paperwork that has to be filled out, courses that have to be taken, etc. And so that is really your guidebook. Again, these are all guidelines and they help to get you there, but again, the graduate advisor and graduate coordinator are individual people that can also be helping you along the way. Right. And there's a whole list of some other resources. So you don't have to Google every single thing that you're looking for. A lot of times you can go here to this website and it's a one-stop shop and you can find a lot of the resources that you need from this single website. Now, I am called the graduate advisor, but in reality, you will have a principal science advisor. We call that the advisor of your committee, or your supervisor or your mentor. So the real person that you will be interacting with for the most part during your graduate work will be that immediate advisor or supervisor or mentor. So there will be a committee. So for the master's degree, there will be a committee composed of several individuals, and the leader of that committee will be your supervisor, your advisor. So for a master's degree, you'll have to complete a master's research project. Again, the focus is on the research project. You will have some coursework requirements as well, and Philip will get into those in a few minutes. But our goal is that within the first or second semester, you've really begun to outline that research project for this 2-year master's program. Part of the master's expectations are that you will submit an abstract and present at a professional scientific meeting at the national level or international level. So you will be the leader, the driver of this research that you're participating in. And ultimately, we hope that you will submit a manuscript for publication in a scientific journal, and then finally finish and defend your master's thesis, and then go on to great things. For PhD students, a little bit longer time frame, typically a 4 or 5 year time frame. And within the first year, hopefully you've begun to define the research project, and you have to, as part of the requirements, come up with a proposal, a research proposal as a PhD student. And you will develop a committee that will have a chair of that committee that will be your direct advisor or supervisor. And that committee will administer this qualifying exam, and you will take a qualifying exam of typically 3 hours, where you are answering questions related to your research project and showing that you are the expert when it comes to the research that you are pursuing for your PhD. Once you pass that exam, you become officially a PhD candidate. So before that exam, you're not officially a candidate, but once you have passed this qualifying exam, you then become a PhD candidate. That is taken in your 3rd semester, or if you already have a master's degree, that would be in your 4th semester. The goal, some expectations as a PhD student, we want you to be publishing your research. We want you submitting manuscripts and getting those published in scientific journals. We then expect not just one, but more than one, several scientific publications from your PhD. And of course, finishing your dissertation and defending your doctoral dissertation research. Now, your supervisor, this is your direct supervisor or your advisor. So they are out to help you. I mean, these are very individualized processes, right? You alone are going to be getting this degree. It has one name on this piece of paper. It's your name, but there's people that help you get there. So it's not a team effort in the sense that a whole team gets a master's degree. It's you individually gets a master's degree or a PhD. So this supervisor has your goals in mind, and they are working with you. They want to meet you where you are in terms of your research interests and your long-term objectives, and what's your professional goal in terms of where do you want to be employed for much of your career. And the supervisor also is there to help you with the research and provide you with timely and instructive guidance along the way. So you're not just entirely working independently all times during the entire program, but you have a resource, your supervisor, that you're coordinating with. And of course, that there's a critical element of respect between you and the supervisor. Now, your role, we don't spoon feed students where we just give them projects and then turn them loose and let them go do their thing. We want students to be engaged in the process. So you as a student will be identifying scientific problems and developing hypotheses that can be tested, that can be identifying the answers to important questions. You will be conducting research actively. Part of research involves communicating that research. So this is technical writing and speaking. You'll learn to write effectively. Scientific writing is a very different process than creative writing. It does involve creativity, but there's also a very deliberate element to scientific writing because we follow the scientific method, follow the science. Have you heard that lately for the last few years? We do that. And develop some depth and breadth. So we don't want you to be an expert in a single topic, but we also don't want you to be a supreme generalist where you know a little bit about everything. We want you to find that sweet spot where you are an expert in a variety of topics, but then also aware of many other elements and issues. So again, I haven't said it yet, but this is very much the start of your professional career. There's this mistaken sense that one does a graduate degree and then afterwards, that's when your professional career starts. I think that's false. I think your professional career starts immediately once you've been admitted to a graduate program. That really is the start of your professional career. You begin acting like a professional the moment you've been admitted to graduate school. So we hope that you consider joining us here at the Jackson School of Geosciences at the University of Texas at Austin. We've got a lot to offer, and we hope that you consider coming to work with us for your master's or PhD. Thanks for your attention.
Then we'll move on to my presentation then. So as Brian has already said, I'm the graduate coordinator for the department. Not the grad advisor, but he won't mind me saying maybe just a little more important than the grad advisor. But anyway, so I'm basically going to tell you about our offers and what goes on academically within the school and the department. I do want to point out that we know some of you may have already been admitted and some of you may not have. So this is the time for everyone to get get involved and talk to prospective supervisors, things like that. That time is going to be determined by you and your prospective supervisor to talk about it and decide when you want to sit down, and whether it's in person, over the phone, in a Zoom conversation, to have a discussion about your program here. Everything you really want to know about our program and about what goes on here. Oh, let me get back. So, as has been explained by the Dean and Brian, there are different units within the Jackson School of Geosciences. We have the department physically here, where I'm sitting right now in the Jackson Geosciences building on campus. Then we have our Institute for Geophysics at the Pickle Research Campus. Pickle, you'll hear a lot. That name, Pickle, actually was the name of a state legislator that the research campus was named after. So Jake Pickle was his name. So we all just call it Pickle or PRC. And then our Bureau of Economic Geology, or the BEG, is also out at Pickle. And then students who are admitted to the Jackson School or to the Department of Geological Sciences can work with anyone in any unit without any difference in support. So remember that once you are admitted into the program, you might start with somebody, you may find out someone else is doing something that interests you maybe a little bit more. And if they're able to, they could take on the role of your supervisor. So again, you're accepted into the program, but anyone, or you can work with anyone. Your mentor is your initial point of contact, the person who it is usually the person who admits you and gets you started in the program. They may or may not end up being your supervisor. You are allowed to switch, like we said. Your research supervisor is the person recognized by the graduate school as the chair of your thesis or dissertation committee. And once you designate your committee, your supervisor takes on the role of mentor. So again, this is usually the person that admits you, but we do have some who will switch between individuals. Let's see. We'll get to that question a little bit later with some of this. Our support offer. So we guarantee support for a master's student for 4 long semesters. A long semester is the fall or spring. A PhD student gets 10 long semesters of support. Again, fall or spring semesters. The salaries that you see there are for RAs and TAs. It's also the same amount for fellowships. Although this is a 9-month salary. So $21,069 for a full year. It tells you there the monthly. That's for a student who has a bachelor's degree already. Students that have come in with a master's will get a slightly higher stipend. And then students who advance to candidacy will actually get a little bit more. Your health benefits are included with both a TA and an RA and on fellowships. And other sources of support include those fellowships that are either in the department, at the institute. The Bureau doesn't have any fellowships at this time, but those students are still eligible for every fellowship offered in the school. And then tuition and fees are paid as well above those amounts. That's something we like to point out, that it's again in excess of your salary or stipend. So we're not giving you an amount in a salary or stipend and then saying, oh, and by the way, you have to pay your tuition and fees with that. We don't do that. So the tuition fees is on top of that, as well as health insurance. So nothing is taken out for health insurance or your tuition from your salary or stipend. Summer support, as I alluded to earlier, summer support is not guaranteed, but we do have several options that exist. TAs for field camp and other summer courses are usually needed. Research assistants in the department, the Bureau, and at UTIG, there are usually plenty of those. There are also industry internships that a lot of students will take during the summer and are gone. The way I like to describe it is no one goes hungry in the summer. Everyone who needs summer support is almost likely to get it. Again, there's these methods here of support, and almost every student has that in one way or another. The other support that is available within the school, we have professional development funds. Those are funds for going to professional meetings, maybe taking a short course or any related activities. Master's students have a budget of $1,000. PhD students have $3,000. That's pretty much available to you as soon as you step in the door. And you just apply or basically fill out forms for it. Once you use it, it is gone. So most students will use it in their later years of their program here because they're going off to present at meetings, things like that. So that's how it gets used most of the time. Off-campus research funds are available to everyone. Students apply to those. They are not guaranteed, but most of a budget can be supported by these off-campus research funds. It's just depending on the budget for each year. And it's support for going to a place that you're doing research out in the field somewhere. Say you need to travel to another state to do some work out there. You apply for it, you submit a budget, and the excuse me, Graduate Admissions and Support Committee goes over it and awards those to students. Then we also have analytical fees support, usually available just in the summers. And again, it is also subject to funding to do on and off campus analytical work during summer again. Okay. So let's step into the degree requirements. For master's students, it's required to have 18 hours, which are 6 courses. Usually most courses are 3-hour courses, semester hour. So 18 hours of graduate geology coursework for a letter grade, then 6 hours or 2 courses of coursework outside of the department. So in any other department besides geo. Then we have 1 semester credit hour of technical sessions. That's basically our speaker series. And then 6 hours of thesis credit that every student has to take in their last 2 semesters. That's a graduate school requirement. Doctoral students, they have 15 hours or 5 courses of graduate geology coursework that they take for a grade. 6 hours like the master students, or 2 courses of coursework outside of the department. And they can be taken on the credit no credit basis for either of these degrees, those outside courses. Again, 1 semester of tech sessions, a proposal writing class that's recommended, and then dissertation hours are sort of like the thesis credit hours for a master's student. That's a graduate school requirement. And then all students coming in have to take Geo 298T. It's basically a how to be a successful graduate student type course, but it does cover a lot of different topics. We're in the process of merging that with the tech sessions and making it a 3-hour course that will probably become effective in the fall of 2023. Things move slowly in a bureaucracy like UT. And so to address the question by Sohini, do we get credits if we have completed certain courses in our master's program, or the course structure is designed as per the department and is mandatory to complete all the courses mentioned? even if some of them are already completed in our previous degree. That is true for PhD students. The course requirements that are listed, or degree requirements listed here on this slide for doctoral students, is an absolute minimum that's required by the graduate school. But in most cases, if you already have a master's degree with plenty of graduate hours, then you, your supervisor, and your committee can decide to count all of that coursework, some of that coursework, or none of that coursework towards your PhD here, and it can be used. So yes, many of the coursework, much of the coursework from a master's degree can be used in your PhD. So a typical degree timeline for a master's student, well, for both, the first semester, you're doing coursework if needed, you're doing teacher training and that 298T that course that I discussed, and then it's starting to explore your thesis options. In your second semester, you will form your supervisor and committee, or form your committee with your supervisor. Masters, you'll start defining your research topics for your thesis. Then that first summer, most people are doing field course and training or some field work of some kind, or like I mentioned before, an internship. Then in the third semester for a PhD student, they're taking their qualifying exam. A master's student is taking in their third semester the first half of thesis, which is 698A, and maybe some other coursework that they're still needing to finish. And then in the second summer, a master's student possibly could be doing some final field work and completing their thesis and 698B. And then a PhD is doing more intensive field work or possibly lab experiments. I should also mention that for the PhD qualifying exam, it's done in the third semester unless a student does not have a master's degree, then it'll be delayed one semester. So you have one extra semester to do that. Okay. That's going to be the last slide about degree requirements and timeline. Did anybody have any questions about that or about any of those? Okay. Then I just wanted to move on to placement. Typically, we have more than 35 companies come through and recruit. We have a career fair each fall. Lately, obviously, it's been a challenge in this pandemic situation. There haven't been as many companies, but they have been doing their own virtual recruiting. And these companies are usually looking for both interns and employees. And these are in industry, they're in environmental companies, they are in other related employment areas, some in Austin even, others just around the world. So during that fall semester, there's a busy schedule of those meetings, interviews, lunches and info sessions. Hopefully we'll get to a full scale of that this coming fall in person. And again, both energy and environmental industries are well represented. We've also had a few other schools looking for PhD students for from our master's population. So we have a lot of people coming through. Our Jackson School students are very popular with employers, so it's always a good thing. And then here are just some statistics from, a 4-year period of 2014 to 2018 of master's student placement. You can see that a big part of them went into the energy industry. A lot are pursuing additional geosciences degrees, and then there are other smaller areas of work from government agencies, environmental companies, things like that. And then our PhDs, their placement, a lot into energy, and almost equal numbers are going into postdoc opportunities. And then academic faculty types are a good part of that as well, and research and government.
So I'm going to introduce the marine geosciences theme, sort of one of 6, general groupings of the research and in some cases also the education that goes on at the Jackson School. Largely speaking, just as sort of an overview here, it's everything from, carbonates to siliciclastic sort of sedimentary processes systems in the coastal and marine environment. There's also lots of tectonic processes associated with convergent margins, rifted margins, transform margins, anything sort of running along plate boundaries near the shorelines or in the deep sea. And this is an area that overlaps very greatly with everything from geohazards to the building of continental margins, and of course a direct linkage to the studies of sea levels change. One of the things that we have available across the school is an incredible range of tools that people can use in their graduate work. Everything from airborne to marine capabilities to study Earth processes. I'll also mention that we have a dedicated field course that is open to graduate students on marine geology and geophysics, which I'll spend a few minutes on. We have a lot of coastal studies tools available to the graduate students. As just an example, here's our own RV Scott Petty, which is a coastal research vessel, can also be used in river environments. And lots of high-resolution imaging tools that students regularly use as part of their graduate work. We have a rapid response program that students have very frequently been involved in, doing things like responding to hurricanes or earthquakes or tsunamis. Here's just an example from studying Hurricane Harvey, where we had groups of students both involved in the airborne LIDAR work, involved in mapping changes on the barrier island systems, and being at sea on the Petty, mapping changes near the barrier islands, and doing things like being able to measure the difference between deposition and erosion before and after the storm related to the effects on the geologic processes locally. Also doing things like responding to major tectonic events. This was actually a landslide event in Alaska, for instance, and this was a map done by the Jackson School that actually mapped the landslide and house-sized blocks that occurred and generated a 192-meter tsunami locally. So these are the sorts of things that are part of the marine program. We have a deep expertise across the school in crustal scale 2D and 3D seismic imaging, and here's just an example of some of the people involved and some cool 3D images off Hikurangi, off New Zealand, where you can see subducting seamounts, and obviously the study here is very focused on geohazards. In addition, we have a lot of opportunities currently for incoming graduate students. One of these opportunities is actually my own and Tip Meckel's, where we're going to be studying the Chicxulub crater with a new ultra-high resolution 3D method using on a Mexican research vessel to study both an existing drill site and a potential future drill site. In addition, Torsten Becker and many colleagues here across the school are working to find students interested in modeling subduction zones and the megathrust, the big subduction zone thrust, to understand how to quantify geohazards in a multidisciplinary modeling and data-driven way. In addition, Peter Flemings, one of our professors here, is actually working directly in the world of the energy transition through a large DOE grant studying methane hydrate reservoirs in deep water settings. You can see a little of the methane hydrate there bubbling away in the upper corner. And just some cool examples of both the 3D data where they're mapping where these things are located and then actually bringing up hydrates in pressure containers and then directly studying them with things like CT through the pressure containers to take a look at what hydrate really looks like inside sediments. We also have a lot of efforts on the climate side, such as studying Greenland and its ice sheets. Its main ice sheet, such as the work here being presented by Benjamin Kiesling, who's going to be a new research scientist joining us, as well as some linkages to environmental justice questions. And then an exciting new development in this world, and I'll play this video, of Rink Glacier in Greenland is a Keck Foundation-funded project that crosses between the department and the Institute for Geophysics and many external collaborators, where the idea is to take an under ice ROV/AUV that runs off fiber optics and send it down underneath this crazily dynamic environment that you can see to study the direct relationship of how sediments coming underneath the glaciers may in fact armor glaciers or resist some of the effects of climate change through these natural sedimentary processes. So this is a cool new upcoming project. Also want to do a quick shout out to the opportunity for education in the summer that is the Marine Geology Geophysics field course that usually has about half graduate students attending, where the students actually get to go and use some of these marine geophysical tools at sea, as well as and directly collect and process the data, as well as learn to do some of the coring and high resolution work like that to mate geology and geophysics, as well as things like grab sampling to sort of ground truth the geophysics that's being collected. And this is a cool shot of a drone being used to map coastal change, launched off the back deck of the Petty. And just some shots of the students doing presentations and processing work and splitting open the cores and things like that. So it's a cool educational opportunity. And this was actually our virtual presentation of all the students, graduate students and undergrads who were involved this year.
My name is Dan Breecker, and I'm going to tell you a little bit about the climate and the environment theme. And one of the things that you've been hearing that I want to re-emphasize here is that, you know, we're divided into these themes, but we're very much integrated across the entire school. And so I was putting together this presentation last night, and I thought maybe a good analogy would be like a circuit board, right? So here's the climate and environment circuit board, actually quite simplified, just in the interest of time. And I've got some nodes on the circuit board there that are all connected by little wires, and that's actually, right, probably a lot more complicated even than this. But the point being that there are multiple circuit boards in the whole JSG machine, and we're all integrated, and there's more connections than we can, right, effectively communicate to you in the short period of time that we have. And actually, I think one of the really exciting things about the Jackson School, and that, you know, you should be thinking about as a prospective student, is that you might be able to create new linkages among us. Actually, a lot of times, a student, becomes the motivation for a new collaboration. So, you know, as you're listening to us talk about these things that are going on in our school, you know, I would try to create linkages and try to, you know, think of what might be an exciting project and joining some of these people together. So oftentimes that's where a lot of big advancements are made, at the boundary between fields. So yeah, I think that's really exciting. And what I'm going to go through is just, you know, a few examples on some of these nodes. So we'll start with climate models, and we're quite strong in this in the Jackson School and in the climate and environment theme. And I'll start with Patrick Heimbach here, who, you know, a lot of text on this slide, but really the what's highlighted in blue here is what's most important. Patrick's focus is to improve our understanding of the role of the ocean, sea ice, and polar ice sheets in the global climate system. And really one of the most uncertain things about the future of our planet is the stability of the ice sheets. And that has a lot to do with exchanges of heat and the circulation of seawater in the polar regions. And so Patrick and his group use a high performance computing to make simulations of the movement of water and ice in these regions. And that also allows me to just bring up that that UT has exceptional resources in high performance computing. In fact, one of the computers is located on the Pickle campus, you know, in the same building as the Bureau of Economic Geology and UTIG. So that's a real advantage. Liang Yang's group studies land and atmosphere exchanges. So there's exchange of water, of course. We're all aware of that, between the atmosphere and the land surface, both by precipitation and by evaporation. But there's also exchanges of carbon, and there's also exchanges of energy, and there's also exchanges of momentum. And Liang's group is focused on developing numerical models to represent these processes in the simplest way possible, such that the models can be applied at every grid scale around the planet. And so his group focuses on, okay, what is the kind of the most essential information that we need to incorporate to get these processes approximately right. And Liang collaborates widely across the school. He's involved with Dev Niyogi, Geeta Prasad, Ashley Matheny, so who are some other scientists in the Jackson School here. Carrie Cook is working on primarily tropical rainfall and effects of climate change on tropical rainfall. So she's, her sort of particular expertise here is to use regional scale climate models. Right? We kind of, many people are aware of kind of GCMs, or global climate models, or general circulation models, some people call them, that simulate climate all over the earth. but there's some disadvantages of using big models like that. And one of them is that the grid scales are too big to represent important processes. So one of the solutions to how to move that forward is to just focus on a smaller area, right? And then there's all these, the boundaries of that area, you need to impose the conditions, and then you can look at smaller scale processes with better resolution and better accuracy. And so Carrie Cook is asking questions about, in particular, tropical rainfall in Africa, and especially in these arid regions where they're sort of like marginal for agriculture. Changes in rainfall in the future are going to be really important in terms of, for instance, the production of food. And then I want to highlight here, you can see I have a connection there between climate models and paleoclimate. I want to highlight something that I think is actually rather unique about the Jackson School, is that we have expertise both in climate modeling and in paleoclimate. And there may be a few other places in the world that do both of those things, but I think we do that particularly well. And so that's one of the unique and exciting things about the Jackson School. So I'll talk a little bit about some of the paleoclimate work that's going on. And of course, that linkage is incredibly important because our climate models actually work quite well for the modern, but what we really want them to be able to do is make better projections of the future when the climate is different than it is today. And so in order to be able to test those models and how well they work in warmer climates, right, we need to look into the past. And so that's where there's an especially strong linkage between paleoclimate and climate modeling. So Tim Shanahan's group is working on this. Tim's expertise, he's a paleoclimatologist, but he's especially good at combining proxy-based reconstructions. And as you can see on the bottom left, here's some data. Actually, this is from a cave in central Texas where he's reconstructing rainfall through time. And combining those proxy data with modeling data, and this is an iterative way to improve our understanding of the way the climate system works, right? The proxy data help improve the model, and the model can inform, perhaps where new proxy data are needed. And we work back and forth between the model and the proxy data. And then, so kind of one example of that is in the top right, where you see a map and the anomalies in rainfall. So the differences in rainfall with a climate change event are shown as the warm and cool colors. And that's compared with the proxy-based evidence for whether the climate got warmer or got wetter or drier. And you see that in some cases there's agreement, but in some cases there's not agreement between the colored symbols and the background map. And it's those places that there's not agreement that actually we kind of tend to focus on and say, well, why? Why is there not agreement there? And how can we better improve the models, or maybe better interpret the proxy data to come to a better agreement and develop a better understanding of how Earth's climate system works. One of the clearly important variables for climate is atmospheric CO2 concentrations. And we have really good records of atmospheric CO2 concentrations from ice cores, but that only extend back about 800,000 years, which of course is just a tiny part of Earth's history. And so there's a very important effort that both Duncan Young and Don Blankenship are involved in, called COLDEX. And you can see on the left over here that the goal of this project is to recover an ice core where we can get a record of atmospheric CO2 and other factors that is greater than 1 million, that extends back greater than 1 million years. And the UTIG part of this is really the geophysical search for that ancient ice. And that really old ice, we know it's there, but the challenge here is finding a continuous section of ice so that the ice can be dated and we have a good chronology so that we can link the measurements in the ice with an age and say something about change through time. So COLDEX is a very exciting ongoing project here. And then I also want to highlight some of Jay Banner's work. Jay Banner does actually a number of different things. He's interested in paleoclimate, primarily from the perspective of how stalagmites in caves record past climate, particularly in Texas. But he also is interested in the impacts of urbanization on water quality. So he's both interested in paleoclimate, but also in climate impacts. And that's especially important in Central Texas here, where Austin has just been growing incredibly quickly. And it's what I consider to be the boundary between the Western and the Eastern United States, right? I mean, in Texas, we have trees, but we also have prickly pear right here in Central Texas. And you go west of here only a few miles, and the vegetation really starts thinning out, and you go east of here and it's much greener. So it's a real boundary. And the combination of rapidly growing population and a kind of like marginally arid climate makes this a really sensitive area. And so the impacts of urbanization on water quality and water availability, not just quality, but availability is really important. And the last thing I want to highlight, we do things in all of these nodes plus others, but only highlighting some of them here. The last thing I want to highlight is carbon sequestration. And the Gulf Coast Carbon Center is working on this. We realize that anthropogenic emissions of atmospheric CO2 are causing climate change, or one of the principal causes of climate change. And so we'd like to figure out some solutions here. What are we going to do about that, right? So in the Jackson School, we study the impacts and the processes in the natural carbon cycle, but we also are asking questions about what are we going to do about climate change? And so this group studies geologic carbon storage. It's the idea being that what we currently do, right, is that when carbon is extracted from fossil fuels, coal or natural gas, it's burned and emitted into the air. And we don't want to do that anymore, right? Instead, we want to collect the CO2 that would otherwise be emitted and then inject it below ground and hopefully keep it there permanently. So there's many components of this that are being studied. One of the perhaps most important ones is to determine, once the CO2 is underground, how can we be sure that it's going to stay there for a long period of time? So the Gulf Coast Carbon Center, Sue Hovorka is the primary contact there, but it's a large group working on many different components of this really important problem.
So my name is Zoltan Sylvester, and I'm a research scientist at the Bureau of Economic Geology. I'm the co-PI of a research group called the Quantitative Plastics Laboratory. And what I want to do today is to give you a flavor of what's going on in terms of energy geoscience research at the Jackson School. And this is not an easy task because there is such a range of people and topics, but I tried to make a list of the broad topics that are relevant to energy research. And these are geophysics and rock physics, carbonate and plastic depositional systems, the stratigraphy and segmentology of these, fluid stress and pressure in the subsurface, faults and fractures, salt and shale tectonics, thermochronology and provenance, carbon sequestration, and more recently, there are efforts going on at the BEG at the Bureau of Economic Geology to kickstart some research groups on hydrogen storage in the subsurface and geothermal energy. And the energy landscape, as you all know, is changing, and that's a good thing. But regardless, which direction this change is going and how fast it's happening, the bottom line is that understanding the subsurface is going to be important. It's going to be important for carbon sequestration, for hydrogen storage, for understanding aquifers and waste disposal, and so on. A lot of the work in terms of energy geoscience at the Jackson School is happening in research groups or research consortia, and I tried to put these on one slide, and I'm not going to cover all of these because we would be here for a long time, but we will just highlight a few projects or research consortia that are taking place. And Dan has already talked briefly about the Gulf Coast Carbon Center group, which is focusing on CO2 sequestration. And this is important primarily in places where you have a power plant, for example, a direct CO2 source, and instead of letting that CO2 into the air, the idea is to inject it into subsurface reservoirs. And apart from geologic characterization of the subsurface, and which includes seismic interpretation, there needs to be monitoring, there needs to be modeling of fluid flow in the subsurface, and this is all happening within the GCCC team. And they have a number of projects across the world, and this is a group that is growing, and they have funding from industry, they have funding from the federal government, and this line of research will be increasingly important. Here is an example that of a project that a master student, Marco Guirola, is undertaking. It's focusing on the longevity of CO2 in faulted sandstone reservoirs in the Gulf of Mexico. And so the idea is how long if we inject CO2 into these faulted sandstones, how long it's going to stay there in a fluid form, or will it leak to the surface through these faults. Another research group and research consortium is called the Gulf of Mexico Basin Depositional Synthesis Project, GBDS. This is at the Institute for Geophysics, and the PI is John Snedden. And what they essentially do is creating an archive of all the geological knowledge about the subsurface of the Gulf of Mexico. And they have put together more than 300 maps with 1,700 layers. And there is still a lot of work to be done. It is amazing to me how little we actually still know about our own backyard, the Gulf of Mexico, and especially the subsurface of the Gulf of Mexico. Moving on to the carbonate group and the Reservoir Characterization Research Lab, or RCRL is the acronym. This is a group that has one of the leading groups when it comes to carbonate sedimentology and understanding of carbonate reservoirs. They do a lot of work in West Texas, in the Guadalupe Mountains, but they also do a lot of subsurface work. And here is an example of well log displays, of well logs displayed in a way that you can really see the stratigraphy. And nowadays, certainly in some of the basins, there are so many well logs, there's so much data that we can really understand the stratigraphy and the geological evolution. The carbonate group also does field work and field trips in places where most people just dream about going on vacations. I want to mention Mrinal Sen's lab. Professor Sen is an expert in computational seismology and exploration geophysics. He has been working on machine learning problems in the geosciences for a time, way before machine learning has become a fashionable subject. And a lot of his funding is coming from the industry, just like Sergei Fomel's group, which is called the Texas Consortium for Computational Seismology. Sergei has been, and his students have been focusing a lot lately on applications of machine learning, especially deep learning, to seismological problems. One of the trends that we have seen in this space is that students who get very familiar with Python and machine learning actually get job offers, not just from the energy industry, but they go to work in the tech industry, companies like Microsoft and Facebook and so on. And here's an example of a convolutional neural network that has been applied to do automatic fault segmentation in three-dimensional seismic data. And you can see how all the different methods that they have tried before are basically left in the dust by this deep learning model that was developed here at UT. Another project I want to mention is funded by NSF and is led by Maria Nicolinacu and Peter Flemings, and it's focusing on modeling and studying upper plate splay faults on accreting sediment. Accreting sediment stress, the impact of upper plate splay faults on accreting sediment stress state, and they are building these sophisticated models to study the distribution of stress and pressure and its changes with fault development. And some of the implications are for seismic and tsunami hazards. Another project led by Peter Flemings and Maria Nicolinacu and others is focusing on what's happening to fluids in the subsurface. And this includes, again, modeling, three-dimensional geomechanical models, looking at outcrops. Here is an example from California of sand injectites in a bunch of mudstone, but also they do experimental work. And this also it links a little bit to the methane project, and it links to overpressures in the subsurface, and it has a lot of practical applications in industry as well. I'm not going to talk a lot about this project called TextNet and CISR. I think Esti will cover it in a bit more detail. The idea is that in order to figure out, in order to understand why seismicity has increased in Texas in recent years, we need to understand both the subsurface and the distribution of these seismic events, and we have to have a good database of those. The Applied Geodynamics Laboratory is probably the #1 research group in the world that focuses on salt tectonics and to some degree shale tectonics as well. And what I'm showing here is an amazing, one of the many amazing experiments that Tim Dooley has run. And what you see here is some silicon putty coming to the surface through a bunch of sediment and forming a salt canopy. And what he also does after making these overhead movies, he slices through the deposits and the salt, which is actually silicone, and you see these beautiful patterns, sedimentary patterns, which are the result of the interaction of the salt with the sediment. And finally, I will say a few words about our research group. It's called the Quantitative Classics Laboratory, and I'm a co-PI with Jake Kovold, but we collaborate a lot with faculty and other researchers. And some of the things we do is looking at classic depositional systems through the lens of 3D seismic surveys. And here is an example of a submarine channel system that has been mapped by one of our students. From the base to the top, you can see how the sinuosity of this channel is increasing, and then we can build fairly precise models of how these things look like in 3D. And we also build numerical forward models of systems that are similar to what you have seen in the seismic. So this is a submarine channel that is grading through time, and it's developing this really complicated 3D geometry. And we also do the same kind of analysis on rivers. Here is an example of 30 years of evolution of the Mamoré River in Bolivia. And finally, we also use machine learning techniques and data science techniques to automate some of the some of the grueling work that a geoscientist needs to do to, for example, correlate well logs. And this is an example of a 3D model from the Permian Basin, where we tied together all these logs to create a better image of the stratigraphy. And two more slides here. One is just highlighting again, Dean Mora mentioned the core research center at PICO, and there's one in Houston as well. Lots of beautiful rock over here, about 700,000 boxes just in Austin. And here is a highlight from the UT Austin Morphodynamics Lab, or David Morig's research group, showing, so this is showing a turbidity current running down through a flume. I have watched these turbidity currents many times in flume experiments, but they are never boring.
Okay, yeah, so I'll be presenting the planetary and geobiology theme. And we've got, ever-growing amounts of research in both of these areas here at UT Austin. Now, obviously, these are two very, very different areas, but as people have mentioned before, there's already many linkages, and of course, there's linkages between the planetary and the geobiology to all the other things that have already been presented. So no matter how you slice it, you're always losing some of the connective tissue. But let's start off with the paleontology. So I'm not a paleontologist, and I will apologize for not presenting this exactly correctly. But what you can see here is that we have a very large paleontology group, right? We have probably 4 to 5 professors and then several researchers and a large group of graduate students that do really cool, amazing work. And judging from this picture, they're a very happy bunch. So Professor Clark has sent me some slides about her research group, and she's interested essentially in the origin of flight and in understanding how animals fly. And so they study both modern birds and they use sophisticated modern technology, for example, like this image of the CT scanner here in the bottom in the middle. They also study vocalization in birds, and I believe one of her recent claims to fame is that she claims that T-Rex doesn't roar, but sort of chirps more like a bird. And of course, they study not just modern birds, they're paleontologists, so they study these very famous fossils of the very first birds that have been found in Solnhofen and in other deposits, trying to understand how flight as a capability emerged in animals. And this is just sort of part of a theme where our paleontologists try to study transitions in the history of life. How did novel behaviors like, becoming a land animal or an air animal evolve? And, what are the structures in the body that are necessary to allow these adaptations? Here are just a bunch more slides. Obviously, there's lots of field work involved, from Mongolia to Antarctica to the northern reaches of Canada, and I'm sure many other places that I'm not aware of. And just like Dan Breecker mentioned in the climate presentation, if you're a modern paleontologist, you need to, of course, integrate many different aspects. You're not just looking at fossils, but there is the sedimentological context of the fossils. There's the geochemical, geobiological indicators. Then, of course, you're trying to bring in the actual biology and ecology of these animals and the phylogeny. And so modern paleontology is a very integrated subject, and it links to many of the other things that we're doing. And so one very nice example, for example, of a link between planetary science and the geobiology at UT is we have paleontologists that study the extinctions and the big extinction throughout the history of life. This is a slide from Rowan Martindale's group. And some of our planetary folks, as you'll see in a bit, study, for example, giant impacts, right? And so there's a link there trying to understand, how the giant impacts affect life, and then how life recovers after this. And that's what's shown on this image on the right there. So you see the megafauna that's all dead, and then there's sort of plankton type animals that begin the recovery of life after a very large impact. I do like the skull and bones. I think that's great. So We also, or Professor Martindale's group also study what she calls exceptionally well-preserved fossils. So these are some of these fossils in these black shales, some of the like the Ediacara fauna, and where you can see very soft tissue preservation. And so that, of course, allows you to study all sorts of details on the birds, on the animals' biology. On the bottom right here is a wild-looking image. And one of the things that our paleontologists use a lot that is a very unique facility is we have a CT scanner that allows us to put very large samples that then allow you to essentially create a CT scanned 3D dimensional object of the, what here must be an exoskeleton of this particular animal. Another thing that you may not know is that, you know, just like we have a lot of rocks stored, we also have a lot of fossils stored together with those rocks. So UT has apparently the 6th largest fossil collection in the US. So if you want to do sort of integrative studies, there's a lot of material right here without need for much travel. And of course, everybody here is involved in outreach. You know, UT has this very nice thing where once a year they bring, it's called Explore UT, where they bring in students from all over the state, and the paleontologists always have a station where here you can clearly see them making bird tracks. A cool thing that Professor Martindale did during in the last few years is she developed an actual board game, I believe, to understand reef ecosystems and their sort of vulnerability and how they evolve. And so here you can see some grad students beta testing this board game. And now we'll transition from, you know, geobiology or paleontology to the planetary sciences with this slide that highlights this X-ray computed tomography facility, because both the planetary scientists and the geobiologists use this. And in fact, many more people also, you know, from people working on subsurface fluids and all sorts of other things. It's really a unique facility. Rich Ketchum is the one who is leading it together with Romy Hanna and other people. And so it's an amazing thing. It essentially allows you to look into rocks and see things, you know, without taking the rock apart. It is now becoming more and more a standard instrument. And we have we're one of the few places that covers both. We can scan very large things. So, you know, if you have a fossil, right, and that's inside of a big rock. So we have one scanner that can take these very large samples. On the other hand, if you want to look at, say, the pore scale, because you're interested in methane hydrates or something like that, you need to have very high resolution, right? And then you need a smaller sample. So we have both a very high resolution scanner that can look in much detail at small samples. And then we have the somewhat this larger scanner that can look at sort of more the fossil sized things. And many cool objects have come to UT. For example, the famous skeleton Lucy of one of the early hominids was scanned here at UT. So now there's a 3D digital representation. And here, of course, you see more. Here you see a meteorite, and you can see these inclusions in the meteorite. Of course, all of this was initially developed for metamorphic petrology to find garnets inside these schists, and it's now being used for ever more applications. And it's something that's really unique to UT. Now, one thing that it will be used for that's extremely exciting, and that's a project that Romy Hanna is leading, is when the OSIRIS-REx mission has already sampled the near-Earth asteroid Bennu, and then next year it will deliver the samples that it's collected from this asteroid back to Earth. And amongst the many things that will be done to these samples is that they will be scanned here at UT. So I have a feeling that might be an exciting PhD project to be involved in right there. But of course, they've used it for many other samples, in particular meteorites. And so it's a really unique opportunity. So we do many more things in planetary science. And so on the geochemical side, we just have a new faculty here, Chen Sun, who studies very large scale planetary science processes from a petrological and geochemical perspective. He's building a experimental petrology laboratory to study things like deep volatile cycles, I apologize, or the thermal history of all sorts of planetary materials, to understand really large scale processes like planetary differentiation, right? How did we go from sort of a near uniform material to something that has a core, a mantle, and a crust, right? So these are very first order questions, in terms of planetary evolution. He's also a specialist in kinetics. So, with sort of high resolution geochemical measurements, you can get very detailed profiles of how elements change across crystals. And from this, you can then do very detailed kinetic and diffusion modeling. And that allows you to get at timescales of geological and planetary processes. Now, one of the, exciting projects that's been going on since, in the last few years is a project led by Gulick, trying to drill into the Chicxulub crater in the Gulf of Mexico and trying to understand really what happened there. And we're just going to indulge with this little video that they made. And I'm just going to play for you.
66 million years ago, the ultimate catastrophe. A massive asteroid slams into the Gulf of Mexico, blasting an enormous crater. The impact wipes out most of the world's known species, including the dinosaurs.
The asteroid impact is the only global instant catastrophe we know of. It happened in a day.
It caused such environmental disaster to our planet that 75% of all life went extinct.
But how did a local event trigger a worldwide cataclysm, killing dinosaurs everywhere? To find out, NOVA is following an extraordinary expedition to drill deep into the asteroid crater.
It's a really big effort on the human scale. People are just really excited about the science.
Science that will reveal new evidence about one of Earth's most devastating catastrophes. The day the dinosaurs died.
So there's grad students right now at UT that are analyzing the rocks from this drill core and trying to understand the hydrothermal systems, for example, that were set up by this impact, to try and understand also the re-emergence of life after the impact and whether impacts can lead to habitable environments on other planetary bodies. So one of our most popular planetary science research groups is led by Tim Gouge, and he is a specialist in essentially remote sensing of planetary surfaces. And he's famous for the work he's doing on Mars, in particular on Jezero crater, where the Perseverance rover is now exploring. And so every year there's grad students that start working with him to try and understand the geologic setting, in particular that delta that the rover is going to be studying. But he's also, of course, applying this remote sensing here on Earth to study the evolution of rivers, for example. And that, of course, links to the kind of work that Zoltan Sylvester has just been presenting. And so there's really exciting stuff to do with Tim now that the rover has landed and we're exploring Jezero crater. Another person that does a lot of, so UT, one of the specialties of UT is that we have a very strong radar group that evolved out of essentially studying glaciers, right? So this was essentially sort of climate change based research. And with radars, you can peek into ice, right? That's why they're involved in this search for the coldest ice. But the same technologies, you can also use radar in particular to study the subsurface of other planetary bodies. And so Cyril Grimmer, who's here on the top right, he is somebody who uses radar to both study climate change on Earth and to study planetary science. And so he's doing radar on Mars to look for ice in the subsurface in a search for water. And actually there is a new project that they just sent me a slide where Sean Gulick and Cyril Grimmer will use radar to study lunar craters. And this is part of the Artemis program that's planning a return of humans to the moon. And the idea here is to combine the surface geological observations with radar to try and understand some of these large impact craters that are on the moon. But to me, one of the more exciting missions that is coming up that UT is involved in, it's the Europa Clipper mission. It's a NASA flagship mission that's going out to Europa, which is one of the Galilean moons of Jupiter. And it's likely the body in the solar system with the largest volume of liquid water, except the liquid water is underneath this rusty ice shell that you can see here. And again, UT's expertise in radar is involved in building essentially the radar instrument on this planetary mission. And the idea is to use the radar to look into the ice and potentially underneath the ice to see how deep it is, how thick the ice shell is, or whether there are any water pockets that are closer to the surface. And there's sort of long-term hopes of eventually sending a lander to maybe sample some of this water and search for life there. So that's, and that mission, I believe, is also launching next year. And there's going to be exciting opportunities for doing really high impact science with the habitability of other planetary bodies. Now, most of this, what I've just discussed, is observational, but people have mentioned that we have a very strong computational group. And so Krista Soderlund is one of our theoreticians that essentially she looks at the dynamics of the oceans inside of these, what we call icy ocean worlds. So inside the moons of Jupiter and Saturn. And so she runs, very large scale numerical models that run for weeks to try and understand, how the rotation and the tidal heating of the planet of these moons affects the ocean dynamics, and then how that couples to the ice shell that we observe above. One thing that is also cool that I didn't know when I came here is that UT has for a long time trained the NASA astronauts. So people are more field oriented, may have an opportunity to get involved with that. And last but not least, so we've, planetary research has been going on for a while at UT, but we've, in the last 2 or 3 years, we've started the Center for Planetary Systems Habitability that tries to bring together the geoscientists and the astronomers with an aim to really fully bring to bear all the expertise that UT has in searching for habitability, both inside our own solar system and with all the exciting discoveries that the astronomers are making with new solar systems and exoplanets that are orbiting other stars.
All right. Okay. So hi, everybody. Yeah, I'm Esti Ukar. I'm a research scientist out at the Bureau, and I am representing the Solid Earth and Tectonic Processes team. We are a large and diverse group of people tackling questions that cover a broad range of topics, from crustal strain and deformation processes, including deep crust, evolution of orogenic belts, fractures, earthquakes, rock fluid interactions, mantle dynamics, melts, magmas, and volcanism, plate tectonics, plate boundaries, and the interaction of tectonic and climate, and many others. All right, so as Philip mentioned, I used to be a student in the department back in the day, and I came from Spain. And there were 2 things that completely blew me away about the Jackson School. And one of them is the amount of opportunity to travel all over the world, both for field trips and as well to conduct field work. And the other one is the range and the quality of analytical equipment and laboratories that we have at the school. And one thing I didn't know before I came here is that graduate students actually get trained to use this equipment, and this can lead to, pretty cool jobs. Once you're done with your degree, you can actually get to run your own lab if that's the way you want to go. So we are a lot of people in this team, and I'm going to just give you a little of a flavor of the kind of things that we do. I'm going to start with Jamie Barnes's group. And so Jamie and her students, I can't see very well. Oops. Jamie and her students do stable isotopes. They look at volatile transport in subduction zones. They study fluid rock interactions and metasomatism and the geochemical cycling. And just to give you a flavor of the kinds of places where Jamie and her students have been working recently, they include the Cyclades and the Alps, Yellowstone, New Mexico, and New Zealand, among others. Next up, we have Liz Catlas, and Liz Catlas and her students combine field laboratory and modeling studies to understand the structure, metamorphism, and geochronology of mountain belts. And Liz and her students actually develop and apply geochemical and geochronological approaches to the study of lithosphere dynamics. And some of the field areas that they have been working on recently are the Carpathians in Slovakia, the Himalayas, and the Menderes Massif in Western Turkey. And so in short, Liz's group combines geochronology, geochemistry, and field-based research to understand the development of mountain belts and the closure of ancient oceans. Okay, next we have Danny Stockley's group, and I'm sure that some of you are familiar with Danny's world-famous UT Cron lab. They are actually one of the best groups in the world doing geo and thermochronology, and they have been involved in projects all over the world: North America, Latin America, Europe, Australia, Africa, Asia, the Caribbean, like you name it. And these are just some of the examples of recent projects that have come out of Danny's group. They have dated the metamorphic soul of the Oman ophiolite. They have used apatite uranium lead to date the opening of the Gulf of Mexico. And one of the latest directions is to actually do uranium lead dating of calcite to know the age of fossils and fracture vein fill, for example. Then we have John Lassiter's group, and John's group integrates major and trace elements and isotopic data from basalts and mantle xenoliths to examine questions regarding the evolution of the Earth. And some of the questions that they try to tackle is: how is continental lithosphere created and destroyed? How much water is in the mantle? When and why did plate tectonics start? And how has it affected the evolution of the mantle? And how do basaltic melts form and evolve at mantle plumes and mid-ocean reaches, and amongst many others. And then we have Rich Ketchum's group, and I think that the lab that Rich has been leading for many years now has been mentioned a couple of times already. So Rich has a lot of expertise in 3D imaging using X-ray CT. And here is what Marc was talking about. This is actually Lucy. It's a 3.2 million year old Australopithecus afarensis human ancestor. And I'm sure most of you have heard about this. Well, Lucy was scanned here in the basement of the department back in 2008. And I was a grad student back then, just, you know, doing my thing in the lab in the basement. And there were security guards everywhere. I was like, what the hell is going on in this place? Well, it was a super secret mission. Lucy was being scanned. I had to learn about this later in the papers, but you know, this is something that is still being talked about today. But the CT lab generates data that involves so many research topics, from meteorics, geology, paleoanthropology, hydrogeology, economic geology, and many others. And because Rich is a multi-talented man, he also works on thermochronology, like fission track dating, as well as thermal history modeling. And then we have Marc Luce's group. I actually did my PhD with Marc, working on the exhumation of blue schist blocks in the Franciscan Melange in California. And so over the years, Marc has had two main research topics. One of them is the subduction channel shear zones that develop at the plate interface. And the other large topic is collisional delamination. So here is some of the work out in California. This is a picture of the Melange with my old office mate, Anna Morisani. And here are some of my beloved blue schist blocks down there. And here is a model of how this very complicated melange actually formed at the plate interface. And here we have some information about how collisional delamination has worked out in New Guinea, where the piping and the tectonics are just right to form these throttling cupulas that lead to the formation of one of the largest porphyry copper ore deposits in the world that we all benefit from. Okay, then we have Jim Gardner's research group, and they actually look at magmas and bubbles within magmas, which are, the erupted kind. So the research is focused on volcanic eruptions and the magma that erupts. And they use field studies, analytical studies, and experimental petrology to understand how these magmas form, they degas, and they explosively erupt. Next up, we have Daniel Truckman, who has joined the department. I was gonna say recently, but it's been a few years now. It's just that this couple of years are so nebulous, right? But Daniel Truckman and his students look at big data and earthquake science. So the Earthquake Science Lab, they address questions like how do earthquakes get started, what causes earthquake ruptures to propagate, and what stops them, how do earthquake rupture properties like stress drop, radiated energy, and directivity change in space and in time. Can we detect and characterize small earthquakes to help us better understand earthquake nucleation fault physics? And do induced earthquakes differ from natural earthquakes? How can we leverage physical and data-driven constraints to improve ground motion prediction and early warning systems, amongst others? And here's just a wide variety of the kind of graphs and data and models that Daniel and his students generate. And then we have Chen San, who has already been mentioned. So Chen, or Dr. San, is a geochemist and a petrologist, and he uses a combination of experimental petrology, field samples, and modeling to study a wide variety of research areas that Marc Hesse has already mentioned. So as you see, like, there is quite a bit of cross between, people in different things, because we do things that are relevant to different topics. Okay, and then we have Afu Lin's research group. Afu is a mineral physicist, and they study all kinds of questions regarding the physical and chemical properties of Earth materials at extreme pressure and temperature conditions. And his group uses high pressure diamond cells coupled with laser and synchrotron X-ray spectroscopies to study geophysics of the mantle and the core, characterize these methane hydrates that have been mentioned a couple of times already, and planetary interiors, and the water and carbon cycles. And Afu's group uses a wide variety of analytical equipment, both small and large, including diamond ambient cells, synchrotrons, impulsive light scattering, Brillouin for the elasticity measurements, as well as micro Raman for phase identification, for example, of those methane hydrates. And then we have Thorsten Becker's group out at the Institute for Geophysics. Thorsten is leading the geodynamics team, where they study the links between Earth's interior and surface systems. Recent projects that they've been working on include the mega thrust earthquake physics and hazards, subduction and erosion in Colombia, vertical land motions in the Cordillera, generation of plate tectonics from mantle convection, and many others. And as it has been mentioned already before, Thorsten Group is actually looking to hire 3 grad students to work on NSF funding projects, and one of them is this project that you already heard about, to model subduction. So get in touch if you're interested in working in anything like this. Okay, and finally, I'm going to move out to the groups that are at the Bureau of Economic Geology. So at the Bureau, many of us are arranged around consortia or research groups, where we have a collaboration between academics and then industry, public and educators, and government and regulators. So one of them is TextNet and CSIR, that Zoltan already mentioned. So TextNet works on earthquake monitoring, and CSIR is the Center for Integrated Seismicity Research. So they monitor, catalog, and analyze earthquakes, employing a backbone seismic network that they have deployed all over the state of Texas. And they study earthquake occurrences, trends, and causes, both natural and anthropogenic. So they have recordings like all over the state of Texas, including the Eagle Ford, Delaware Basin, Midland Basin, the Panhandle, and the Fort Worth Basin. And as you have seen before, there has been quite an increase in the amount of earthquakes that have been occurring in Texas in recent years. And these are related to different causes, and they occur in different settings, including basement heights, oil fields, structural simple basins, structural complex basins. And they have concluded that injection above basement rocks, as well as hydraulic fracturing, are actually a main cause of these earthquakes in Texas. So this is quite a scary slide with lots of words, but just so that you get an idea of the kind of disciplines, research partners, and research topics that are involved in this kind of research, which I think is absolutely exciting. Another one of the groups is the Salt Tectonics group that has also been mentioned before. This HEL group is the leading group of salt tectonics research in the world. They've been studying salt tectonics for several decades now, when salt tectonics wasn't even a thing. And as you can imagine, in the Gulf of Mexico, for example, this is absolutely essential. And so HEL uses very different approaches, from field mapping to 3D and 2D numerical modeling, and these physical models that Zoltan was showcasing to study salt tectonics. And more recently, they have also been applying similar strategies to work on shale tectonics. So looking at shale diagenesis, finite element modeling, field work, seismic modeling, physical modeling, and all kinds of other things. And last but not least is the group that I'm involved with, which is the Fracture Research and Application Consortium. And we actually looked at fracture rocks. So we want to understand how fractures form and evolve. And historically, we've been doing a lot of work in oil and gas, but as you can imagine, fractured rocks are very important for many topics, many of which actually are essential to the energy transition. So we are getting more and more involved in geothermal energy regions, CCUS, hydrogen storage, economic geology, and many others. And we are a multidisciplinary team, also using many approaches to tackle these questions, from field studies, analytical work, using SEM, fluid inclusions, hydrothermal experiments, and lots of modeling, geochemical and hydraulic fracture modeling, to understand how these fractures form and evolve, and how they are going to behave in many of these systems that are going to be essential in the very near future.
Hi, everyone. How are we doing out there? I know you can't respond to me, but you can use the chat. We are so glad that you're here with us, and I'm really happy to share with you some of the work that's going on related to surface and hydrologic processes at the Jackson School. Please engage with us, type questions. We're here to also learn about you, and I'm so sorry that we aren't able to see you in person this year. So the surface hydrologic processes theme covers, you can think of it maybe as like the fluid earth or the sedimentary record and what it says about earth history and the water cycle, contemporary water cycle processes. Here's a bunch of definitions of ways that we define this theme. And my name, I should say, is Daniella Rempe. I'm a professor here in the Department of Geological Sciences. My contact info is right there if you want to get in touch with me. And so I'm going to give you kind of a whirlwind tour through what we do and contributions that we make to society and to the state of knowledge. We are a group of geomorphologists, sedimentologists, stratigraphers, hydrologists, glaciologists, geochemists, atmospheric scientists, geophysicists, and critical zone scientists. Some of us identify that way. I know some of you out there identify that way. And so we are focused on all sorts of different processes relating the water cycle and its interactions with the shallow parts of the crust. And so I'm showing you here a couple of fun examples. We have Professor Catania, who's up in the studies glaciers, a glaciologist. We look at high alpine lakes and sediment transport processes in mountainous regions. We look at fluvial geomorphology in mountainous regions and in big floodplains and deltas. Look at aeolian processes and lakes in deserts and arid regions. We even look at submarine processes that transport sediment. And so here are some examples of folks out in the field in their domain doing their thing. We keep going. Okay, I guess we have a lot of people doing lots of different things. One thing that I want to emphasize is that we acknowledge the interactions between humans and the water cycle and the movement of sediment across our surface. So many of us are engaged in research that's tackling issues related to our society and its sustainability. And so here's just a bunch of examples from a recent paper that really highlights the role of humans as agents of change or as important parts of the hydrologic cycle or the water cycle specifically. And so you see impacts to, for example, submarine groundwater discharge and the impacts of pumping on coasts. We have folks working on that. Changes to the sediment fluxes that are coming out of rivers and how that affects deltas and their formation. Ways in which precipitation is changing due to changes in evapotranspiration and the distribution of ecosystems in montane regions. And so these are just examples of ways in which we're incorporating humans into our study of a natural system. And so it's something that we just have to acknowledge, and we're doing here at the Jackson School. And in this theme, we also are considering fluxes of important nutrients. So that includes thinking about the carbon cycle, the nitrogen cycle, and its relationship to the water cycle and the movement of mass across the crust. And so I'm going to walk through a couple of really fun examples of research at the Jackson School to just give you an idea of the breadth of types of research that we do and how diverse our approaches are. And I'll show you here two examples of flooding. So on one hand, we think about how we can store floodwaters and mitigate the risks associated with infrastructure damage during flooding. How can we use water banking to save water, mitigate risks, and address flooding in Texas? And then on the other hand, we have Mars over here. How did flooding impact landscape evolution on Mars and the sedimentary record that we see on Mars? How do we interpret it in the light of processes associated with flooding? Trees. I'm here, shown on the left here, stuck up in a tree. I look at trees to think about how they impact the subsurface, how they mobilize nutrients and sediment and are impacting carbon cycling and the rate of transport and weathering of hill slope material. And on the right, we have Ashley Matheny, Professor Matheny, in a paper that she wrote with a graduate student and Professor Liang Yang in our department, looking upwards. So how are trees impacting atmospheric dynamics? How are trees impacting our ability to, and fluxes, I should say, water fluxes through trees, transpiration, impacting our ability to predict future climate and respond. We use sophisticated sensor networks for a variety of different projects. I'm showing two here where Michael Young at the Bureau of Economic Geology is leading a sensor network to look at soil moisture storage called TEXON, Texas Soil Observing Network. And then we have in the bottom here, Professor Dave Naogi, who is sensing heat across Austin to better understand how Austin serves as an urban heat island and what we can do about making our cities cooler. We use fun technology at the base of glaciers here on the left. This is a project recently funded project of Professor Ginny Catania's looking at the melt rate at the base of glaciers at the terminus where they meet the ocean. and using these really interesting robots to get at better rates so that we better understand sea level rise. So on the right, we're looking at the impacts. We have a project out at the Bureau of Economic Geology, looking at the impacts of sea level rise on sand resources. And so while these things seem super disconnected at the Jackson School, all these various faculty and researchers and graduate students at the heart of that are making big impacts and drawing large connections across these different diverse fields. On the left here, we're looking at the impacts of drought, the 2011 drought in Texas that had strong implications for future climate states as shown by climate models run here at UT by Professor Yang's group. And on the right, we're showing how I've drilled into a hill slope and one of our attendees here has participated in this research to better understand how drought impacts, for example, landsliding and fire risk and sediment transport risks or changes associated with drought. And so we're looking at drought from a number of different angles. And then finally here, we're looking at sediment transport at the base of glaciers to better understand how they're moving. And we're looking at sediment transport in rivers using these really cool electronic traced rocks in Professor Joel Johnson's group so that we can understand how climate change is affecting sediment transport and mass movement. I guess we have one more. Here we go. We have an example of submarine, of trying to better understand submarine transport on the left-hand side in a large flume, one of our huge flumes that's been mentioned before. And on the right, we're looking at transport via melting of permafrost in the Arctic. And so now I want to transition into telling you about some of the resources we have, many of which you've heard about. So this includes a bunch of flumes. We can do physical experiments and we can make observations about processes that we know are occurring at much larger scales and with much more complex interactions. And we can try to isolate those interactions in a lab setting. And we do that across a number of different scales. Very exciting work by our morphodynamics researchers. We also use, as has been mentioned before, airborne remote sensing in a number of different platforms, a number of different tools. An example here is a drone that's used out at the White Outdoor Learning Center, which is another resource that we have for us nearby. We have a piece of property that we're establishing research infrastructure and that's available to graduate students to do research. And so we have a number of different techniques for detecting the surface, like LiDAR, structure for motion imaging from things like drones, as pictured here with Professor Tim Gouge. And we have a number of different sensors that we put onto either drones or planes. We have lots of geophysical tools, some of which you've heard, but we use a variety of near surface geophysics tools to better understand water cycling in the near surface. Here are some examples of electrical resistivity tomography or nuclear magnetic resonance or neutron logging. And we even have our own drill rigs in some cases. And so we probe, sense, can detect below ground processes using a variety of tools. You've already heard about CT, the CT facility. We use it in the surface and hydrologic processes theme. I'm just showing an example here of looking at fractures and microfractures in a rock that is part of a root zone. So we want to better understand how plants can access water from rocks like this. And then no matter where we sample water, gases, sediment, we have a variety of facilities that students can have access to and learn about and use that are very unique at the Jackson School. We have the ability to, for example, look at mid-mass stable isotopes. We have a unique facility that allows us to look at, for example, lithium isotopes that fractionate with clay formation. This is a very exciting new direction. And so there are various researchers that are using that tool at the Jackson School to understand systems like paleoclimate and the modern impacts of rock weathering. You've already heard about TAC, the largest, I think this is still true, the largest university supercomputer in the world. Many of our students have access or use this in their research. And so now I'm going to transition into telling you about some courses that we offer. And I find this to be one of the more unique aspects of the Jackson School when I talk to our alums that go off to do things like work at NASA or national labs or various government agencies like the Forest Service or the USGS or in academic research institutions or in industry, the training that they got here is very unique. It not only includes access to exciting and interesting field sites and techniques, but also computational resources and training in, for example, numerical modeling, machine learning that that have served them quite well in their career. So here's an example of our karst hydrogeology class, and also an example of how we partner with local agencies. Pictured in the middle here is Marc, who's an adjunct professor in our department and also director of research at the Edwards Aquifer Authority. And so these are images from his karst hydrogeology class where we learn about local hydrogeology and also just carbonate systems and their and all of the sedimentary deposits associated with, for example, cave drip and the signals that we might learn about our climate from looking at, for example, speleothems here. So this is the karst hydrogeology class. We have the groundwater field camp that we run every summer. We do a variety of things like drill and look at core and try to characterize aquifer properties using both the core and geophysics. Is a very unique opportunity for students. We do tracer tests in water bodies like this one shown here. The water here is not usually this kind of neon pink. And we go out and do geophysics for various research projects associated with hydrofield camp. And so it's an opportunity for hands-on experiential learning for our graduate students and learning techniques that they might use in their research or they might use or want access to later on. And so I find it to be a really enriching experience for our graduate students that, that focus on hydrologic processes. We also have a number of courses that cover things like, in the bottom right, I'm showing a sensor developed by Nicola Tosado's group that's used to, well, right now I think they've deployed it near our stadium, and they're looking at impacts of loading of that stadium during during football games. But that's an example. I'm just showing it here as something that Professor Tosado's class helps students learn how to build. It's an environmental sensing class where students literally build sensors for their research. And one of my own students, for example, learned how to build from scratch a sap flow sensor in that class. At the top, I'm showing a bunch of pieces of the mass spec because we have a class that allows students to learn how to run their own samples and understand the fundamentals of mass spectrometry so that they're equipped to eventually not just run their own samples, but potentially go on to run their own labs. And then in the bottom left, I'm just showing an example from a soils characterization lab from one of our classes. We have a lot of opportunities to learn techniques that we use in our research within the framework of our courses. And finally, another example of that is that we have courses on remote sensing, courses on using Python in your research. We even have a course called Preparing Future Faculty that helps you prepare applications for academia and better understand whether you want to go into academia and what that entails. So I'm showing here images from various courses on radar remote sensing, on hydrology, where we use remote sensing products. And on the right, we have research from Gita Prasad's lab, where she is incorporating visualization of climate data into her coursework. So you'll have access to all of these types of skills here at the Jackson School. And I also want to highlight, finally, that we have lots of partnerships which provide lots of great opportunities for our students who do internships during the time scale of their graduate degree program or afterwards. And these partnerships have both enhanced their research and also their career opportunities later on. And so here are just a couple of them. For example, I'm associated, or I have an affiliation with the UT Center for Space Research because of some of the remote sensing and gravity work that I do. And I also work with Edwards Aquifer Authority. And we have lots of partnerships with national labs who are increasingly interested in better understanding the evolving water cycle and carbon cycle. And so these are just a couple of examples. And with that, I will happily take questions and hook them. Thanks y'all for being part of this today.